Hey everybody, welcome back to Kerbal Space Program. This is a little different from what I normally do here. I'm actually making this video to try and help explain some of the aspects of orbital mechanics in more layman's terms. I'm going to try to do some of the math, but I was just exposed to it Wednesday and it hasn't quite fully set. Even though I've played this game for years and I can do pretty much anything that you would have to, I don't really do it mathematically. I just do it using the tools provided in the game, which is kind of the one of the better aspects of Kerbal Space Program is they give you those generalized tools. This is actually being made for my engineering physics class. If there's anybody in there who is interested in watching it, otherwise I still want it to kind of fit with the channel in general. But we are doing a lab in my engineering physics class where we're flying a simulated space shuttle mission to the International Space Station in Orbiter 2010. I am not using Orbiter because I have some concerns that just kind of showing how to play it as a game would kind of circumvent the point of the lab, which is not to actually make a successful rendezvous, it's to make sure you got your math right. And so if I kind of show little piloting tricks for getting around, say, wrong calculations and stuff, I really think I'm going against the intent of the lab. So, Kerbal Space Program it is. Just a few things right off the bat for people not familiar with Kerbal Space Program is that the planet I'm launching from is much smaller than Earth. Delta V requirements are much lower, burn times are shorter, even the massive stuff is a lot different. Right now, sitting on the launch pad, this thing weighs about 320 tons. When it's empty, it weighs about 40, which is very light, and in fact, dimensionally, it is smaller than the real space shuttle. Everything's just scaled to it. And not to get into too much detail about the shuttle, but just some interesting things about the real space shuttle that I can explain with this. The OMS system right here, these were actually self-contained pods. You had fuel pumps, fuel lines, and the engines attached to this pylon. And once the shuttle came back from a mission, these were removed as a unit for service and repair. I can't really do that in this game because I don't have the patience to turn those into fuel tanks. And so my OMS fuel system is fed through this tank right here, which I have to turn off for this other consideration I've had to take into account, which is the real space shuttle, the first third of the tank held the liquid oxygen and the other 2/3 was the liquid hydrogen. And liquid oxygen being much more dense, the center of mass for the primary fuel tank is actually pretty well concentrated up here because the mass difference between oxygen and hydrogen is so great. I can't really sort this out and have everything pumped correctly without losing my mind, and so I just take a simplified system. By locking all the other tanks, I go into the fuel balancer and I just make sure that everything is constantly pumping into the top tank. There we go. And that will keep the center of mass moving forward as opposed to, draining from the top to the bottom, which is standard in Kerbal Space Program, which would throw off the center of mass. And eventually, once it came back far enough, these engines would be shooting past the center of mass and just causing a flip and generally bad day. That's pretty much all the considerations that I really want to get into right now. So I'm going to pause this recording and then restart it, just so I don't lose this explanation in case the launch goes terribly wrong. And I'm back. The first consideration I need to take into account is figuring out what I want to do for my launch as far as what my initial parameters are going to be. With the station behind me, I'm going to try to set on a slightly higher track than the station itself is on so that it will catch up to me instead of me chasing it around at a lower altitude. That may change. By the time I'm in orbit, this may end up being ahead of me. So I'm going to have to make that call on the fly. But right now the plan is to get on a slightly higher orbit. I'm obviously exaggerating with my mouse here. So that this will kind of drift into the shuttle instead of having to make pretty wild plane changes to get at it. And at this point in the recording, my voice got drowned out by the solid rocket boosters, so there really wasn't a lot relevant to anything we're talking about in the lab for this section. So I'm just going to have a brief musical interlude while we watch me hand fly this thing into space. Wanting to try to keep this around between 30 seconds and a minute until I get to the altitude that I want to be. I'm probably going to boost this thing up to about 230 kilometers and then switch over to the OMS pods to do the rest of my burn. In real life, the tank would be completely dry and empty at 90 kilometers. Obviously, I can get away with a lot more, and when I play this just for my own satisfaction and for my video series, I don't actually do OMS 1 burn. I set my apoaps on the main engines and try to get as much out of it as I can. Now, thrust to weight ratio is above 1. Bring the nose down really low. Set it on the horizon and just let that count down, because the closer I am to the apoaps, the faster I'm raising my periaps, and that kind of keeps me on a circular ascent profile, because this thing will not handle a hyperbolic launch very well, like at all. barely chasing that apoapse around. I'm just, once again, eyeballing this. The real computer software and programming that goes into planning a ascent profile is so far beyond what I am capable of doing that I just kind of have to play it by ear here. I'm still in the atmosphere, so this is still a suborbital launch. If there were no atmosphere, this would be in orbit. Alright, so at 230 kilometers apoapse, I'm going to switch this back to free view because orbital camera is really not all that helpful. The periapse, my lowest point in my orbit, is actually still in the atmosphere, which is good because when I jettison the tank, that means this will be aero captured and not stay in orbit where it can be potential debris to run into. I'm still in the atmosphere. In this game, the Kármán line, which separates the official designation of what separates space from atmospheric flight, is 70 kilometers, and it's a hard cutoff in the game. In real life, they're like even the ISS at 400 kilometers roughly is still technically in the atmosphere and still experiences atmospheric drag that has to be compensated against with the occasional I guess maintenance burn. I don't think that's not the correct word, but I'm not going to time warp out of the atmosphere. I'm just going to wait to get out because time warp within atmosphere gets a little buggy sometimes. But I'm getting there very quickly. My vertical speed is 102 meters per second, which is pretty dang fast. 63 kilometers. Once I get out of the atmosphere, I'm going to rotate belly down. I'm going to dump the tank, and then I'm going to line up and push this. Actually, I'm going to check my orbit here. I'm moving much faster than the station, so I am going to boost this apoapse high, and then put myself on a bigger track so the station has a chance to catch up to me. Just waiting for the and there we go, past the boundary. I am going to make judicious use of time warp throughout this video because it can get really tedious. Trying to wait for everything to happen. Since the main engines are not needed, I'm going to go ahead and shut them down. As I previously said, in real life, the tank would be totally dry at this stage, but this thing's a lot more efficient than the real shuttle was, so I've got quite a bit of fuel left. It's always nice to kind of have that fudge factor on anything. Alright, gonna get nose level to the horizon, turn on stabilization, and then separate from the tank. And I'm gonna give a couple RCS puffs just to get some good separation, to make sure I do. Going to open up the cargo bay doors, and turn on the lights, and then I'm gonna pitch up 15 degrees above my prograde vector. There we go. And then I'm going to unlock the fuel tank so that I can complete my burn. And there we go. And now these little things will carry me up to my final altitude. I think I'm going to aim for probably... I'm going to start with 290 and see how that gets me. And if I check the map, it'll show my rendezvous. I will be here at my first closest approach, and the station will be here. So, in the game, you actually have a way of very easily calculating a maneuver change. I am actually going to try to do this mathematically. And I'm going to, if I get a good equation, I'm going to put the, I'm going to put it up on the screen in post-production, but I'm actually going to pause right now, and I'm going to run through the math and see if I can get something that makes, a little bit of sense to get my periapts raised up to circularized. So, just going to step away for a minute and be right back. Okay, and now for the actual math portion of this. I originally did a voiceover of the video while it was running. This is well after the fact, just because I wasn't happy with the audio quality, and I kind of made the math sound a lot more complicated than it really is. And so I'm going to simplify things and show you where to find what you need on the readouts. But I am going to show you how to calculate things like your orbital radius and your semi-major axis, if you're curious and if you're not using Kerbal Engineer. But in Orbiter, you will always have your semi-major axis available to you. So as far as the lab goes, this is going to be actually simpler than I'm making it sound. So just bear with me. I kind of enjoy the math of this, and that's the only reason why I'm going into it. The very first thing you need to find is your standard gravitational parameter, which I can go through all the steps to simplify the equation from Newton's second law and all that stuff, or I can just give you the final simplified form, which is what I'm going to do. The final simplified form to find your standard gravitational parameter, which is designated by the Greek letter mu, which is that funky looking U shape, is acceleration of gravity times the radius of the planet squared. So in this case, we're going to have 9.81 meters per second times 600,000 meters, which is 600 kilometers. That gives us a mu value of 3.53 times 10 to the 12th. From that, you can use that to find your current orbital velocity by plugging it into your current orbital velocity at apoapsis. So what you end up with is your velocity equals the square root of mu times 2 over your orbital radius minus 1 over the semi-major axis. Obviously, semi-major axis is up here in Flight Engineer, and they give it as 778,210 meters. The way you calculate that is you add your apoaps and your periaps together, you divide that value by 2, and then just add your orbital radius. Very simple math, and orbital radius is just your apoapsis altitude added to the planetary radius. Because you're measuring your orbital radius from the center of the point mass, which is whatever planet you happen to be orbiting, plus your altitude, instead of just your altitude. And so going through all of that, we end up with mu times 2 over 891,819 meters minus 1 over 778,210 meters. When you do all that math, you get the velocity equals the square root of 3,333,625, which itself comes out to 1,825 meters per second. That is your current, and I'm not sure if that's average velocity or if that's velocity of the apoaps. I think I checked it, and I think it's average, but in whatever case, this is the value you need to help calculate your delta V. Very same operation when you find your desired orbital velocity, what you want it to be after your circularization burn, and the 2 over orbital radius stays constant, and to find 1 over your semi-major axis, you basically put what you want your semi-major axis to be, which is just apoapsis times 2, then divided by 2. So it's really just apoapsis plus the orbital radius of the planet. Jeez, got lost there. And that gives us V equals the square root of 3,920,000, which comes to 1,979 meters per second. At that stage, it's a very simple subtraction problem to find your delta V, which you just take the desired velocity, subtract it from your current velocity, and we get a total delta V change of 154 meters per second. And I'm actually pretty happy with the explanation I have in here for finding your burn time. So I'm going to switch back to the old voiceover and let that explanation stand. So now that you know how much faster you need to accelerate at the apoapse, you need to take your vehicle's capabilities in mind so you can find out how long that burn is going to take. And the equation for this is very simple. It's mass times delta V equals force times delta T. And this is where Kerbal Engineer comes in really handy. My current mass is 43,924 kilograms. In real life, I would have to take into account the weight of the fuel I'm burning, but the mass of that is so insignificant compared to the rest of the ship that it's not going to throw the calculations off too much. Just flying this by hand is going to throw it off much more than the amount of fuel I'll be burning. So, from there, 924 kilograms times a delta V of 154 meters per second times a force of 170 kilonewtons. Yes. And times delta T. From there, you multiply the mass times your delta V and then divide your kilonewtons out. But if I were to go 43,924 times 154 and then just divide by 170, I get a huge number that is definitely not correct. When you do your kilonewtons correction, for this instance, I'm doing 43,924 times 154 divided by 170,000. And that gives me a burn length of 39.7899764,706 seconds. Basically 40 seconds worth of burn. Now, one of the things I like about Kerbal Space Program is with the maneuver node system, there's a way to double check myself. I can come out here, add a maneuver, and I'm just going to set my velocity to my delta V to 154 and see what time it gives me to make sure I did my math correct. So let this creep up, and at At 154 meters per second delta V, my apoapse should be 297,399 meters, and my periapse becomes 291,798. That is probably because I wasn't taking into account the fuel burn, and plus that, just 1/10 of a meter of a second actually makes quite a significant difference. Okay, not that big a difference. But that's pretty darn close, and I've been assured that in the lab we're not going to have to calculate the mass of the fuel burn, so there's that. So yeah, I'm pretty happy with that. I'm going to delete this, and we're going to do a blind, not necessarily blind burn, but a full manual delta V change. I'm going to watch my time to apoapse. When it gets down to 2 minutes, I'm going to come out of time warp, and I'm going to start orienting for the burn. Actually, when I get down to 1 minute. And so I'm going to want to start my burn probably about 20 seconds before I cross the apoapse. I'm going to correctly orient the shuttle too. In reality, the cargo bay doors were kept facing Earth. Turn on stability management and then finish this. And so we have time to apoapse, 30 seconds. Once again, having to orient the nose above the horizon to about 15 degrees. And this is where it's going to be very important in the lab to keep track of the burn length. This is actually doing a pretty good job of it because I'm going to stop my burn roughly 20 seconds after the apoapse. And in fact, I'm going to cover up my... Well, okay, I guess I can't do that. And it looks like I need to manually keep track of that because the apoapse will change. So, looks like I had a significant variation, probably due to the mass of the fuel being burned. I really don't know how they're going to cancel that calculation out in Orbiter unless he's going to have us fly with unlimited fuel. I don't really think he's going to be doing that. It's been a while since I've messed with Orbiter, so I don't really know what the plan is. But eccentricity is still very low. My current orbital velocity is 1,994 meters per second, which I will have to wait till I get to my apoapse, because that's what I have my speed calculated at. So we're going to time warp to the apoapse. 1,968. So not exact, but I got ballpark, which flying this thing manually, especially because I'm not entirely certain I have the nose on the correct perfect vector. So I'm thinking I'm putting a little radial variation into my orbit too. However, for a manual burn, without using the maneuver node system, that's actually pretty dang good. And this is, from what I understand, this is about all we're going to be asked to do in the lab. I think the launch window is going to be handled by the simulation, because in reality, to make a launch rendezvous window, you need something called a pork chop plot, which is something that a supercomputer chews on for, you know, a couple days to find out the exact ideal launch conditions to reach your target. So I really don't think... and he also told us we're not going to worry about a rendezvous. So for what it's worth, I think that's all we've got as far as the purview of the lab goes. I am going to go ahead and dock this for entertainment value, but if you're just here for the math and to kind of see how things work, actually, I need to go into time warp and show how this is going to catch up to me, because it's on the shorter track. That was a little too fast. And I can do that by going to my rendezvous readout, picking and my intercept distance. You can see that's just crawling down constantly because I'm moving slower in relation to the space station. You can see it's closing that distance. Down to 500 kilometers. $350. And this is all without burning any fuel. And this rendezvous is going to be something called a Hohmann transfer orbit, which we have not even touched in class. So I'm fairly certain that he's not going to require us to do the math on this. It's been a very long time since I've even tried to calculate one of those, and I've never done one correctly. So that part of the math I will have to cover in a later video, probably long after I've finished this physics class. Now I am 50 kilometers away. I should actually be able to see it. There we go. Right here. 33.2 kilometers from the target. Now, the easiest way to affect a rendezvous is going to be to bring the nose down here. And then start bringing my apoaps and periaps down. Or actually just mess with the periaps. Okay. And this is just blind, seat of the pants type burning. See that intercept distance getting gradually closer. I'm probably going to wait for intercept 2. This is not the most efficient way of doing things, but once again, I don't have the math skills I really need at my disposal. So we are going to warp around to that rendezvous. I really do want to calculate these with a Hohmann transfer orbit at some point, but that's going to take a lot more practice in math than I currently have available to me right now. Once again, this is Engineering Physics 1, so, and who knows, we may cover it by the end of the year. If not, it's definitely something I'm going to learn on my own. I'm going to go ahead and match my velocity to the target. What is my separation here? Let's see. Just changing my RCS burn right now, or I'm burning on RCS, which is the reaction control jets, those little bitty thrusters that are all over the ship. I really don't think this was an option for the real shuttle, but I am outside the purview of our lab, and therefore I can do what I want. Alright, so I've got a 1.4 kilometer separation there. My relative velocity is 7.9 meters per second. So that's going to be a much slower and gentler rendezvous than I'm actually used to seeing here. So Just going to drift in. I'll wait as it loads into physics range. Hopefully it won't crash. Which reminds me, I'm going to do a quick save here just to cover my bases. I'm going to go ahead and start adjusting my trajectory, trying to push that flight path marker over the target to kind of get me onto an intercept course. I do need to be careful and watch my intercept distance though, because if it gets to 0, then I'm within 100 meters of it, and that could very easily lead to an accidental collision. So I hope everybody found this informative and at least a little entertaining. So I'm just going to leave it here. I'm going to crank up the time warp and put on a little music and just let this video finish out. Thanks for hanging in there with me, and happy flying.